Okay, and the final little bit that we need to deal with in terms of integrating and finding areas is that we also actually can integrate parametrics. And I mean, this is true in general, but obviously one of the major applications of integration is to find areas under curves. So if we want to deal with integrating parametrics, we need to just step back and think about what's being asked of us and exactly how we're going to tackle it. Because let's just have a look at example 24. What we have is a parametric curve where x is t times 1 plus t, and y is 1 over 1 plus t. So I've got my parametric equations here. T's got to be bigger than 0, that's absolutely fine. And we've got a graph sketched of this, which is kind of helpful. So this is what my curve looks like. And I want to find the area of this region here underneath the curve, bounded by the curve and the x-axis and the lines x is 0 and x is 2. So this is the region I want. And what we would do ordinarily is we would just integrate between 0 and 2 y with respect to x. And that's absolutely fine and easy to do if we have an equation for y in terms of x, but we don't. This equation is in terms of our parameter t. At this point, we have two basic choices. I can either attempt to rewrite y as a function of x, so do a bit of work replacing this t here with something to do with x, or I can change my integral that I'm tackling. Now in this case, in this question, I don't actually have a choice. I have to deal with my integral because this is a quadratic. And because it's a quadratic, it is actually an absolute nightmare to try and rewrite y in terms of t, because it just doesn't work nicely, because I've got t and t squared. T appears twice in my equation. It's a quadratic. There's more than one solution for this. So in order to do the substitution, it just would be awkward, particularly compared to what we can do with our integral. So in this case, I need to change and modify my integral so that it doesn't have x anywhere in here. Now, rewriting an integral without a letter, like swapping a letter out for another, that feels an awful lot like the technique we tackled earlier in the chapter called substitution. And in fact, that's exactly what it is. We just need to reorganize this equation so that instead of having x's, we have references to t. And the way we do that is by remembering the chain rule. Dx, actually we can rewrite as dx by dt, dt. So I can rewrite this as the integral between, well actually I need to think about my limits in just a second, but it's the integral of y multiplied by dx by dt. I can figure that out in just a minute with respect to t, my parameter. Now, I need to deal with the variable change because when x is 0 and 2, those are my limits, t is not 0 and 2. So I have to change the limits, just like we did when we were doing substitution. So when x is 0, this equation is 0, so t could be 0 or negative 1, but we know t can't be negative 1, so t must be 0. When x is 2, I have 2 equals t plus t squared, or rather t squared plus t minus 2 equals 0. That's a quadratic that we can solve relatively quickly and find that t could be 1. There is a second solution, but it's negative. So t is 1. So I'm actually integrating between 0 and 1 now because I have changed my variable from x to t. There's only one thing I need to do now, as I need to rewrite this without y's and dx's in here. I just want to write a function of t in this integral. So I know y is 1 plus 1 over 1 plus t. I also need to know dx by dt. Well, x equals t plus t squared. So if I differentiate that, I get 1 plus 2t. And now I have everything I need to pull this all together and then deal with the integration. So I am integrating between 0 and 1. Instead of y, I have 1 over 1 plus t. Instead of dx by dt, I have 1 plus 2t, and that is with respect to t, my parameter. Hopefully we can see that this can be tidied up a little bit more than this. So this is the integral between 0 and 1 of 1 plus 2t over 1 plus t with respect to t. And at this point, I've converted everything into an integral that I can do nice and easily. If we were being asked to demonstrate what's going on, we would do a bit more work pulling that apart and integrating it. However, I can also just apply my calculator to this problem. Bearing in mind the calculator is dx, so I need to just think in my head agilely about this, and where I see a t I need to write an x so that the calculator will interpret it correctly. So what I want is 1 plus 2x over 1 plus x integrating between 0 and 1. This is a little confusing because of what's going on, because obviously we've converted everything to t and then I'm typing x's in, but I've got 1.307. 1.307. Now I'm just going to scroll back up to the question. This says find the exact area of region R. So in this instance, my calculator has failed me because this is not exact. This is a decimal number. And hopefully you will recognize that this is one of those integrals that we can do using natural logs. So we actually need to do a bit more work. We can't rely on the calculator, although we can use that value to double check our final answer. So we're going to have to do a bit more work in order to actually properly integrate this. And that extra thing we need to do is partial fractions. So what I want to do is I want to do 2t plus 1 divided by t plus 1. I'll just put the variable in front because it makes life easier. I can see that I can subtract 2t plus 2 from here for 2 lots. And that leaves us with -1. So it's 2 lots, remainder -1. So our actual integral, split into partial fractions, is the integral between 0 and 1 of 2 take away 1 over 1 plus t with respect to time. And that's a fairly straightforward thing to integrate. Integrating 2 is going to give us 2t. And integrating 1 over 1 plus t is going to give us ln of 1 plus t. And that is between 0 and 1. So if we substitute our limits in, then what I have is, if I substitute in 1, this is going to be 2 minus ln of 1 plus 1, which is 2. Take away, if I substitute in 0, this is 0 minus ln of 1. Natural log of 1 is 0, so this is all gone. So my final answer is 2 minus natural log of 2. And I can double check that on the calculator. 2 minus natural log of 2 equals 1.307, and that's the number we got earlier from doing the numerical calculation. So I'm happy that that's exactly the right answer, having pulled it apart into partial fractions and then done the integration. The key point to remember is that we can rewrite our integral with our parameter as the variable instead of x, but just like when we did substitution and definite integrals, it also means changing the limits. So we need to be very careful about where we do that.